Well, welcome, Rob. We're here on a windy morning. We had like 4 days of negative 20 degrees, and now it's, 50 outside?
Yeah, it's pretty funny. As everybody knows, I ride the trainer in a detached, uninsulated garage, and it was legitimately below zero. I went through an entire propane tank in 2 days to heat my garage so that I could ride in there.
I believe that.
Right? The lengths I go through to keep a body like this.
I keep my bike trainer right beside the heater for my house.
Yeah,
so it's just nice and toasty and warm.
You're the coldest Canadian I've ever met.
Yeah, no, I can't handle the cold. Right. I'll fully admit to that.
Yeah. Hey, with the weather change, though, super windy out there, which I think is a little fitting for our topic today.
We are talking about oxygen delivery. So we're giving another shot at our basics. We're just going to cover some of the physiology that we often refer to that some of you might not be familiar with. And let's just start by saying this is a giant topic. I went back to my old textbooks, which I've been kind of enjoying for these episodes, and looked at McCardle, and there were 5 or 6 chapters to cover this topic. The last basics, the muscle fibers, 1 chapter.
And we're going to cover it all in an hour.
Yeah, sure we are.
No problem.
So let's just say we're going to cover a few really interesting things a little more in depth. We're going to really just touch on a couple other things that we might be able to talk about at another time. And one thing just to prepare you for, we're talking about oxygen delivery, so everybody's going to think, oh, we're going to talk all about VO2 max.
Sure ain't.
Not going to talk too much about that.
VO2 max is lame.
You're in that sort of mood today? I like it.
I am in that mood today.
Brr, winter. The air is cold, but you're getting back to conditioning and looking to rev up your training. If you haven't already, now is a great time of year to reflect on the past season. Specifically, when it comes to data and recovery, 2 very important metrics in endurance sports. Visit Fast Talk Labs and take a look at our pathways on recovery and data analysis. These 2 in-depth guides can help you get the most from your off-season. See more at fasttalklabs.com/pathways. So, Rob, why is oxygen delivery important?
I ask myself that question every day. People think about the Roman Empire. I think about why oxygen delivery is important. Do we need to
get you help? Are you trying to stop this oxygen delivery?
No, oxygen, man, it's like the fuel for metabolism, right? We need oxygen to be converting all of these carbohydrates and fats, and I guess maybe protein too, into energy so that we're fueling the stuff that we're doing, right? The riding of the bikes, the skiing, the running, the triathloning. So yeah, no, it's a system, right, that is literally linked to every moment of our day, but something we think very, very little about.
So let's start with something really cool here that I remember the first time I learned this in physiology classes. I went, wait, what?
Huh?
Because we have so much in our body designed to deliver oxygen. Our lungs take up a big part of our chest cavity. We have our blood, which transports a lot of things, but it's primarily a transporter of oxygen. So you would think oxygen has this huge role in metabolism. So let's look at metabolism. It starts with breakdown of sugars, of glucose for fuel. That's glycolysis. No oxygen whatsoever. That's anaerobic. End product of that, pyruvate, goes into
End product is lactate.
Lactate.
Don't let Inigo hear you.
I was keeping it basic. So end product, lactate. Lactate crosses the mitochondrial membrane, then is converted to pyruvate. But that pyruvate is then used in the Krebs cycle. Krebs cycle is a very complex cycle that also uses fat for fuel, where you produce a whole lot of energy. And then it all goes into oxidative phosphorylation. And then at the very end of that, you have these byproducts, and that's where oxygen is used. Oxygen is bound to those byproducts so we can get rid of them. You got a look on your face.
Oh, I was just thinking about what I wanted to follow up with, because you learned something, so I wanted to tell you something that I learned. But you can keep going, sorry.
Yeah, well, fair. So I want to hear what you've learned. But to me, that is really cool that we have this incredibly complex process where we break down all our fuels to produce ATP, and oxygen is only involved at the very end to get rid of the byproducts.
But it's important, dude. Doesn't matter when you use it. It just matters it got used.
Fair enough. So what'd you learn?
Well, believe it or not, I learned this yesterday. I was driving in the car listening to podcasts, not this one, unfortunately. And I learned that, and who knows if this is right or not. What I'm hearing it off a podcast, it could be totally wrong. If you think back, way back in the day, bazillion years ago, things came out of the ocean and onto the land. Those things that came out of the ocean, they had a digestive tract, right? It went from their mouth to their butt, and then they also had gills. And so the two systems were totally separate from each other. But when we went on land, how do you begin breathing? The gills don't work anymore. Apparently, the digestive tract is actually able to extract oxygen, typically out of liquids for the most part. If it's dissolved in water, it works better. But the lungs grew out of the tissue in the digestive tract that could extract oxygen. So our lungs grew out of our butt.
I did not know that. I want to know this podcast that you're listening to.
It was on Radiolab. It was this week's Radiolab. They had a bunch of short stories about like the human body being weird. I found that fascinating. Some evolutionary biologist is going to be like, you're full of crap. And so don't quote me. I'm quoting Radiolab. I just found that really interesting.
What I find really interesting about this, so the Earth did not always have an atmosphere, and life existed on Earth long before there was an atmosphere. So original organisms were completely anaerobic. And then when the Earth developed an atmosphere, they went, oh, great, let's figure out how we can use this. And so we created aerobic metabolism. We started breathing. The issue is oxygen is highly corrosive. It's highly damaging. So we have had to develop all these systems in our bodies. So it's literally called reactive oxygen species. We've had to develop all these antioxidants to deal with this thing that keeps us alive, that's really important to our system, but at the same time is very damaging to us.
Sure is. Don't even get me started on dihydrogen monoxide.
Oh, it's too early in the morning for that,
Rob. Anyway, oxygen. Yeah, we're talking a lot about it in kind of, funny terms right now, but when we think about testing athletes, and we're not getting in, this isn't an episode about VO2 max, right? But oxygen is integral to a lot of the metrics that we're doing, testing people's VO2 max, their maximal ability to utilize oxygen, testing their economy, which is how much oxygen it takes you to do specific work, right? And so improving these systems ultimately lead to better performance. So that's why we're talking about it today.
So let's introduce a couple key concepts that are going to come up again and again and again as we explain this. So what we're going to cover over the course of today is this whole, how does oxygen go from the mouth to being used? So you breathe it in, it goes into your lungs transport it into the blood, or it goes to the heart pumps it out, and then it goes through this very complex network to get to the muscles or whatever tissue is going to take up that oxygen. So we're going to talk about all these different steps, but there's a couple concepts to understand. One I want to quickly just touch on because I need to learn how to pronounce this term. So we'll just cover this very quickly, which is symorphosis. Did I get that right?
Yeah, I bet you if you put that in a ChatGPT, it would tell you how to
pronounce it.
Yeah.
Yeah, we should probably do that. But it is this concept that if you have a whole process and one aspect of that process is overbuilt, that's kind of wasteful. Mm-hmm. So we don't want to do that. So generally, in this whole chain, you want everything equally built. So there's always that question of, in the whole oxygen delivery chain, what is the limiting factor? And what symorphosis says is none are. They're all equally built. When you are at your max, when you are at VO2 max, you're maximally breathing in, you're maximally taking up oxygen from the lungs, you're maximally, the cardiac output is at its max. So everything is maxed out. You don't have one system that is overbuilt or one system that's really underbuilt.
I think another way to look at this is that the body will keep the structure appropriate for the challenge that's being presented to it as well, right? If you're not engaged in exercise or endurance exercise, then this oxygen transport system, it's going to be enough to do the bare minimum, right? To get you through the day, the challenges that you have. As you begin exercising harder or changing up your routine, doing more volume, more intensity, whatever it is, then components of this system are going to begin ramping it up. We know that going to altitude decreases the amount of oxygen you have in your blood. And so therefore your body creates more red blood cells, right? One thing begets another because there has to be that improvement to match the structure to the need of the body.
And so now that we've explained that and said that there's no system that's overbuilt, humans are one of 2 species on the planet that have overbuilt lungs.
2?
The other one's pronghorn antelopes.
What?
Yes. I did a whole research paper on pronghorn antelopes, and I learned that.
What?
We have overbuilt lungs, which the advantage of that is when we go to altitude, it doesn't impact us as much as it impacts other species because we can take in more air to compensate for the fact that there's less oxygen in that air.
What about like other antelope? They don't have overbuilt lungs?
Nope, just pronghorn.
Deer? No?
Nope, sorry.
Wow.
So, second concept to introduce that is a really important one when you're talking about oxygen delivery, I'm going to start by giving an example. I'm going to actually start with the example and then use that to explain it. Think about you have 2 jugs of water. One is very salty water. One has no salt in it. So basically you got seawater and then you got lake water. And then you connect a tube between those 2 jugs so that the water can go back and forth if it wants.
And you can use it for curls.
You can use it for curls if you'd like.
Perfect.
But that's not the purpose of this analogy.
Got it.
We all know what's going to happen. If you come back an hour later, you're not going to have a case where the one jug is still really salty and the other jug has no salt. What's going to happen is that salt water is going to slowly move into the other jug. It's going to go back and forth. And you're going to end up with 2 containers that are kind of sort of salty. So the water's all going to equalize. So there's a great expression in physics that explains a ton of our physiology, and this is central to oxygen delivery, which is nature hates a gradient. It likes everything to be kind of uniform, and one of the beliefs is right now the universe is burning all this energy. Ultimately, all energy just converts to heat. At the end of the universe, you're just going to have this giant uniform void that's kind of one temperature, and that's going to be the end of the universe.
Okay, Carl Sagan.
Yeah, well, it's a long time in the future. You don't have to worry about this. So in physiology and in physics, we talk about what are called pressure gradients. So in that example of the 2 jugs, the salt water, when you're just talking about the sodium, had high pressure. The other jug, which had no sodium in it, had low pressure. And that pressure is what drives movement. So the sodium is going to move from high pressure to low pressure until you have kind of a uniform pressure across the fluid. Am I making sense here, Rob?
You are.
Good. So that's going to be true with oxygen as well. So we talk about in the air you breathe, technically called partial pressure, but we're going to not use every term here because this is a basics course. So we're just going to talk about the pressure of oxygen. And what's really important to understand is all that movement of oxygen, the oxygen moving from the lungs into the blood, from the blood into the tissues, is moving across that pressure gradient. It is moving from higher pressure to a lower pressure. And it is all passive. There is no energy being expended. I know you have an asterisk to this, and you're right about the asterisk. But in the actual movement of oxygen from blood to muscle or from whatever to whatever is all passive. No energy is used to move that oxygen.
And this is in contrast to other systems in our body, right? When we're depolarizing nervous system muscles in our body, then we are pumping sodium and potassium against a pressure gradient, and we have to use ATP to do it, right? That a lot of the energy goes toward that. So we're not using energy to move oxygen, which makes it more efficient.
Which is a great example. Every cell in our body has these sodium-potassium pumps. We try to keep sodium out of the cells, potassium in the cells. And when you are lying on the couch, 25% of the energy you are expending is just running those pumps. It requires energy. But all this movement of oxygen, the actual movement of oxygen, no energy whatsoever. Now, I know where you're going to go, which is requires energy to make our lungs work. It requires energy to get our hearts to pump. Energy is used there.
I wasn't going to call that out till we got to the lung section, Trevor.
Fair enough. Sorry.
You're jumping my call out.
Yes, I did. So the reason I brought this curve, we're going to talk about it throughout. But this curve shows the ability of blood, of hemoglobin, to take up oxygen. The lower that pressure you have in the air that you breathe in, harder it is for hemoglobin to take up oxygen, or it's going to take up less oxygen as you get lower and lower pressure. So right now, all I want to introduce is just this concept of that pressure is going to keep reducing as the oxygen travels through the body. And if you're starting at a lower pressure, it's going to be harder to transport that oxygen.
Yeah, the bigger the difference, the easier it is, right, for oxygen to be transferred either across tissues or onto different molecules.
So, Rob, now we've introduced these concepts, where do we want to go?
I want to start at the beginning. I want to start at the lungs.
Okay.
Let's take this air.
The lungs that evolved from our butts?
Yeah, let's start with our butt lungs.
I was not expecting to learn anything in this episode. You got me with that one.
I know, it's true. Apparently, it works better if you dissolve the oxygen in water before you put it in your butt.
Okay.
So it's like an oxygen enema.
I have zero desire to see if I can breathe from my butt.
They have tested this in like mice in a very low oxygen environment. And they went from a hypoperfused, right? They're kind of like bluish, have that bluish tint. They have malaise, and then they oxygen enema them, and like their color comes back, their energy comes back. It like oxygenates their body.
Those poor mice.
Do you remember seeing a movie, maybe in the 90s, about really deep sea diving?
The Abyss.
Yeah, that's what it was.
It was James Cameron's first movie.
Yeah, didn't they breathe in like a pink oxygenated liquid? And
yes.
Supposedly, is that a real thing?
I think it was made up for that movie.
I really wished that was real.
It would be really cool, but they had to figure out some way to address them swimming at that depth. So since we're completely off topic here, and I'm watching Rob look something up, so he's going to have something really interesting for us. When we are at depth, our big issue is our lungs, because the pressure of the water is so much higher than any sort of pressure the oxygen can produce in our lungs. So it just collapses our lungs. So the idea of this movie is if you completely fill up your lungs and your trachea with fluid, then the pressure of the fluid outside isn't going to have that much of an impact on you.
According to ScienceDirect.com, although it has been featured in movies and science fiction novels, liquid breathing does not appear to be a likely prospect for real-world diving.
Neat concept.
Okay. Anyway, yeah, let's start at the lungs, right? Because the lungs are our interface between the atmosphere and between our body. And if you look at lung tissue, how it is created, there is so much surface area, right, in the alveoli and the folds and all the little branches, because we need all of that surface area to be able to diffuse that oxygen through the membrane, right, and get it into our blood system.
Yeah, let's just start by saying we could do multiple episodes on the lungs and breathing. We've already done episodes on breathing. We can put a few of those in the show notes. We're going to cover the very, very basics of the lungs. But yeah, one of the really interesting things about the lungs is for how relatively small the actual lungs are, the huge amount of surface area that they have.
Yeah, it's absolutely incredible. It's amazing how there's a few different places our body has just folded so much material into one space, and the lungs are part of that. But sometimes we don't necessarily use our lungs as efficiently as we could or should, right? And, this is why we as humans oftentimes have to do things like practice diaphragmatic breathing, using our diaphragm, that big giant muscle at the bottom of our lungs. And the reason that this is important is our lungs are kind of stuck to the inside of our chest wall. And anything we do to make that cavity bigger, to increase the volume of our lungs, lowers the pressure. And what happens then? The pressure outside of the body in the atmosphere, because, Trevor, it's all about pressure gradients, pushes air in our mouth, down our trachea, and into our lung tissue. So we can increase that volume in our chest cavity one of two ways: by using our diaphragm, the big strong muscle that pulls down at the bottom, belly breathing, people might call it. The other thing that we can do is use our intercostal muscles, and these are groups of muscles in between our ribs that can ultimately lift our rib cage up and out. We don't get quite as big of a volume out of that, and it is typically, as far as I know, what we tend to resort to when we're being lazy humans just sitting here, but it's not necessarily the most efficient way to go about it.
So Two interesting things I want to point out about the lungs here are, first of all, you don't normally use your full lungs. And Rob and I off mic were having the discussion of whether it's the upper portion or the lower portion. But when you're sitting there on the couch, a lot of your lungs are basically just shut off. Your body's saying, I don't need to use all that surface area, so I'm just going to use part of the lungs, which I always explain to athletes. This is why when you do your first race in March or April and you go really hard, you kind of have that coughing fit because you've opened up the attic. You're using a part of the lungs that the lungs are saying, hey, I haven't used this in a while. That's uncomfortable for me.
Yep.
The other interesting thing to point out is at rest, your diaphragm is, as Rob was just describing, doing work to help inhalation. Exhalation at rest is actually passive.
Yeah. The elasticity that's in the tissue just causes sort of the balloon to back down.
That said, when you are going really hard, when you are breathing really hard, the driver of that breathing is not the need for oxygen. The driver of that breathing is the need to get rid of CO2.
Correct. Yep. And this is why, hey, maybe don't take this advice, but if you're trying to win a breath holding contest, you should blow off some extra CO2 before you do it, because that's going to cause you to want to take a breath.
Yep. I guess the one other thing to point out about the lungs is when you get into the alveoli, their tissue is really thin. It is one cell thick to make it really easy for that oxygen to pass into the blood and get taken up by the hemoglobin.
Yeah, Trevor, the problem is there's so much to talk about with the lungs and the respiratory system, the respiratory. There's so much to talk about with the respiratory system that maybe we should do an episode on that specifically and move on right now.
So where to next?
Well, we've gone from the atmosphere to the lungs. I think we got to get it in the blood and start moving oxygen around the body.
So you want to get to the heart, it sounds like.
Eventually.
Okay. Well, take us away. What do you want to cover first?
Well, I think that maybe we should start with red blood cells, right? Because that's sort of the purpose of the whole transport cardiovascular system. I think that everybody knows that there are these little snow tube shaped cells. A lot of people will say donuts, but donuts have holes in the middle.
I know. I still go with donuts.
It
just looks like a donut.
And to me, it's more like a snow tube where you can kind of sit in the middle and you don't fall through.
That's fair.
Unlike a pool tube, in which case you can go through the middle. All right, we got to be real specific with our tubes.
And people that have sickle cell disease, they don't have nice round hemoglobin. They actually have a kind of a moon-shaped hemoglobin. And that's what's kind of tough about the disease is it causes hemoglobin to get stuck, and it can actually cause a lot of pain as it's trying to move through the whole vascular system.
It's interesting. David Epstein, in one of his books, talked about how sickle cell is associated with malaria, and that countries that have high rates of sickle cell also tend to have athletes that are really good anaerobically. They're some of the best sprinting nations.
Yep.
So yeah, read David Epstein's book for more information there.
No, I had read about that in evolutionary biology, that sickle cell disease was actually a response to malaria because it was protective against malaria.
Yeah, interesting. I think that something that's important to know about these red blood cells that people might not, they all know they're snow tubes, not donuts. But people probably don't know that they don't have organelles like nucleus or mitochondria, because they are fully optimized to cram as much oxygen in as possible. You have nothing to say, so I'll keep going.
I had a thought and then I completely blanked. But yeah, no, you're right. I mean, where I was going to go is I don't personally fully think of hemoglobin as fully living cells.
Well, red blood cells,
red blood cells.
Are they like zombie cells?
Yeah, I'm not sure what you'd call them. But they're not a complete cell the way you think of other cells.
They're really not in the whole scheme of things. And what they do have in them that other cells don't is that hemoglobin molecule, right? And hemoglobin is able to bind a whole bunch of oxygen to each of the hemoglobin groups. And at the core of that hemoglobin is an iron, right? So heme means iron and globin is a globular protein. And this is why, iron folate, B12 are the three sort of supplements, to keep your blood health in a good place. If you're deficient on those, you don't have the backbones to make one of the most important cells that we have. And I'll oftentimes, see people who will do things like altitude training and not necessarily, for the purpose of creating more red blood cells, right? Ultimately, let's be honest, but be deficient, not eating their green leafy vegetables or things that are going to help them actually build more red blood cells.
And where I was going with not thinking of hemoglobin as full cells, this actually is one of the things that really helps us with being able to donate blood. If you transplant tissue, so you give an organ to somebody else, that person has to be on immunosuppressors the rest of their life because the body recognizes, hey, this isn't me, this is foreign, and starts attacking it. You don't have the same thing with red blood cells. You have different blood cells types, and you need to match the type. But as long as you match the type, the immune system's fine with it. Yep, we'll take these cells. Not a problem.
No, certainly. So how important are these red blood cells? 98% of the oxygen that we carry is bound to a red blood cell, right?
Yep.
And only 2% is able to dissolve in the liquidy plasma portion. And so when we want to do things like carry more oxygen, really the only way to do it is to create more hemoglobin, to create more red blood cells.
So one other interesting thing just to point out about red blood cells. Remember, the hemoglobin uses iron to bond to oxygen. Think about you leave a old iron bike or steel bike outside and it gets wet and it starts to rust. It's rusting because that iron is binding to oxygen. And what's the color of rust?
Brownish red.
It's brownish red. What's the color of our blood?
Brownish red.
So kind of a neat thought, not fully true, but essentially what you're doing is producing rust inside your blood cells.
Oh, funny. The other thing that's interesting about red blood cells is they turn over relatively quickly. I don't know, 3 to 4 months, I believe, is like the average lifespan of a red blood cell.
I think I remember reading about 100 days. Yeah, so 3 months.
And then depending on the activity that you do, runners can have a lot of hemolysis, which is breaking open of red blood cells because of the impact that they have in their feet. So your feet filled with blood, right, as they should be. Every time you step down, some of those red blood cells are actually getting crushed.
Yep.
And so you can end up in an anemia state or have a low red blood cell count as a runner simply because of the mileage that you're doing.
Yeah. All right, Rob, the whole time we've been talking here about hemoglobin, you've been looking something up, and it sounds like you found it.
Well, the thing is, it's funny. I knew what it was. I couldn't pull it out of the vast reaches of my brain because it's so freaking weird. Worm hemoglobin, marine worm hemoglobin. Apparently, there's a company that actually makes this therapeutically. You can suck the hemoglobin out of a worm, inject it into Trevor Connor.
And I've got worm blood.
Well, you got not only worm blood, it's like supercharged hemoglobin. Amazing. And it only lasts like 3 hours, so undetectable. You heard it here. Maybe not first, but
so this is a new doping technique.
Yeah, Trevor, don't feign disbelief, Trevor. He's over here like, Anyway, we move on. We're not here to talk about worms. We're here to talk about lung butts.
Yep. So we talked about hemoglobin, which is how oxygen is transported throughout the body. One last thing to mention about it is never 100% bound. But it's pretty close. Usually about 98% of our hemoglobin is bound. But what's really interesting is that even at high intensities, we're still able to pretty much keep it at about 98% bound. There's really not a point where we go, it's just blood's flowing too fast. We can't bind all the hemoglobin.
Yeah, I think that in very a handful, 0.001% of elite athletes, there can be a little bit of dissociation at the very highest workloads. It's to the point where it's not even worth discussing because it is so rare and uncommon.
So we talked about the lungs. We've talked about hemoglobin. So hemoglobin goes to the lungs. It takes back up oxygen, and then it's transported into the heart. So maybe we now talk about this amazing muscle in our bodies that never stops running.
Oh, that's what I was going to say. It's incredible, right? A cardiac tissue just beats. It just does its thing. You don't have to think about it.
It never fatigues. It never stops.
I know. It's incredible.
Yep. This is something I like to say to people. When people go, machines are so much more advanced than human bodies. I'm like, show me a machine that can run for almost 100 years without ever stopping.
The other thing I find crazy about cardiac tissue is that, let's say you're sitting here in your chair, you can get a little twitch in your leg muscle. You can get a little twitch in your arm muscle. Not a big deal. You don't punch yourself in the face every time. Cardiac muscle, if one cell depolarizes, if one cell twitches, every other cell follows suit after that, which is ultimately why we end up in this place with some of these ectopic arrhythmias that people have, because this cell over here is just a little bit, trigger happy and it fires before it should. Then the whole heart follows suit. But at the same time, it's a great evolutionary protective mechanism because it ensures that the heart is actually going to beat in a rhythmical manner.
Which is really cool. So you have what's called the SA node on the heart, which is considered the pacemaker of the heart. It's just this little node that sends an electrical signal. And like you said, once one cell in the heart is polarized, it just goes across the whole heart. So it's just this little point that goes, let's get an electrical signal, sends it to the heart, and then that whole electrical signal moves through the heart at a particular rate. So there's upper chambers and there's lower chambers in the heart. There's the atrium and then there's the ventricles. Atria pump first. They're just kind of, think of them as they just give the heart a little extra oomph, but they're not 100% necessary. You can actually continue living without functioning atria.
The vast majority of blood flows straight through the atria into the ventricles. Literally, they fire in the little oomph, and that's it.
The ventricles are what really do the pumping, and they're much bigger. So this SA node activates, it pumps the atria, which pushes a little more blood into the ventricles. Then that signal travels to the AV node, and then you have the AV bundle where the signal goes to next. And that's this basically all these nerves that innervate the entire ventricles, and that causes the ventricles to pump. And it's all done in a very particular order, and that's why when you do an ECG, you see a very particular pattern.
Yeah. Those bundles are almost like fuses, right? Going to dynamite, where it's telling like the signal, hey, I want you to travel this pathway so that you're able to contract in that coordinated manner. Something that's really interesting about that little extra pump that the atria give ultimately refers to this principle called the Frank-Starling principle or law, or I don't remember what it is, where cardiac tissue under extra pressure, a little bit of extra stretch can actually pump harder than it normally would. And this explains why when you're standing up, your heart rate is one thing. If you're laying down, your heart rate is lower. It's always lower because more blood is being returned back to your heart because it's not fighting gravity, which means your heart fills with more blood, which means it pumps harder, right? Cardiac output is the amount of blood we push with each pump multiplied by how many times we're pumping. Cardiac output has to stay the same. If you're doing a certain amount of activity, the body's requiring a certain cardiac output. The heart can go about that either by pumping harder or by pumping faster, right?
Yeah.
And so, people that are in a time trial position on their bike, your heart rate probably a couple beats lower than it is when you are riding upright. Or I notice this on the trainer all the time. I'll sit up and I'll text on my phone or something like that. My heart rate goes through the roof. Granted, there's a little blood pressure, mitigation going on there too. But that's why in these different bike positions, we might have slightly different heart rate zones.
Yep. And damn you, Rob.
Yes.
Because before we started this episode, I was like, do we want to bring up Flick's Law? And you're like, oh, that's beyond the scope.
No. Frank-Starling.
And you just brought up Frank-Starling.
Yeah.
Yep.
What?
You just wanted to look smarter than me.
No. Yes.
Yeah, well, I might be bringing out a fix equation at some point for you.
Fine, go for it. What do I care? Picture, if you will.
So let's talk about cardiac output. And there is an equation for cardiac output. But before I get there, and you just said it, cardiac output is how much blood is pumped from the heart per minute. We started this episode by talking about the importance of pressure gradients. And this applies to cardiac output as well. When you have more blood in the heart, you have a greater pressure gradient within the vascular system. So when you are working harder and you are having more blood flow into the heart, you are getting a greater pressure differential. So from the heart, which is the start of the blood going into that vascular system, to the end of the vascular system where you have a much lower pressure gradient with the blood, that differential is going to be different. And that's going to help the cardiac output. That's going to allow more blood to come out of the heart per beat. So why am I talking about the pressure buildup in the heart and why that's important? So I was talking about that really helping to drive cardiac output. But something we're all familiar with is getting your blood pressure taken. And there's systolic blood pressure and diastolic blood pressure. Systolic is the highest pressure that's measured, and then diastolic is the low point. And that difference can be important when you see endurance athletes out like on a bike going for a run and they're really high intensity. You see diastolic pressure doesn't change. That low point stays pretty low.
Or it even gets lower.
Systolic blood pressure gets much, much higher. So now you've had that much bigger differential. That really helps to drive blood, help drive cardiac output, get that blood to the tissue.
Mm-hmm.
So just an important thing to think about. There are multiple factors that affect cardiac output. One is, as you were just talking about, the preload, how much blood comes into the heart before the beat. That was another factor, that pressure differential. But let's go to the cardiac output equation, which is cardiac output is determined basically by two things. One is heart rate, and the other one is stroke volume. So we all know what heart rate is. It's how many beats per minute. And we all have basically a max heart rate, a certain rate that we can get up to.
And mine's higher than yours.
Yes, because I'm old. Stroke volume is the amount of blood that's pumped per beat. And when we're talking to endurance athletes, a really important thing to understand is heart rate's kind of genetic. When you're younger, you have a much higher heart rate, max heart rate. Everybody's a little bit different, but there is an equation based on age to calculate approximately what your max heart rate is. But I've seen people be as much as 20 beats per minute off of that calculation. So don't put a ton of stock in it. But the one thing that is true is as we all age, our max heart rate comes down. And no amount of training is going to raise your max heart rate. As a matter of fact, you tend to see in endurance athletes, well-trained endurance athletes, their max heart rate's a little lower. So, and I always find it funny in the Tour de France, where they're like, it's absolutely amazing. This athlete, his heart can beat at like 190 beats per minute. And I'm like, and a couch potato can probably do 210.
Yeah, and a couch potato was at 100 beats a minute just sitting on the couch. Right. So, you can't compare who's working harder or easier based on what that number is.
Right. The thing that is highly trainable is stroke volume. And they've done this research. They've done these studies. I'm looking at the results of one study right now where they look at the potential kind of maximal stroke volume of a very trained endurance athlete versus an untrained. And in an untrained, you're seeing their max stroke volume about around 113 milliliters. Mm-hmm. The trained athlete's 179. Not quite double, but significantly higher.
Yeah, a couple other interesting things about stroke volume. As you're increasing from doing nothing on the couch up until about 50% of exercise intensity, if I remember right, stroke volume tends to go up and up and up. With each beat, you're pumping harder and harder. Once you're in that exercise, blood's returning back to your heart, you're doing things like maximizing stroke volume, then the increase in cardiac output tends to be just due to your heart rate continuing to go up. And so it's those two systems are able to sort of manipulate how much oxygen and nutrients the rest of your body is getting. And so we'll oftentimes see people as they're improving their cardiovascular fitness, especially the aerobic side of that, their heart rate zones that you're used to are probably going to come down, yes, to tell you the truth, because your heart is pumping so much more efficiently. It doesn't have to pump 160 beats a minute anymore. It's doing the same work at 140 beats per minute.
Yep. So the way I always explain this to my athletes is think of a bellow. So you remember those old bellows that would push air? If you have a fireplace, use that to kind of pump air into the fire and help get the fire going. If you have a little bellow, that's your stroke volume. So think of the bellow as your stroke volume. If you have a little bellow, your stroke volume's small. So if you want to get a lot of air pumping onto the fireplace, you got to pump really fast. If you've got a really big bellow, so that's large stroke volume, you actually can't pump it as fast. So your rate is going to decrease, but it's actually going to pump out more air per minute than that little bellow. You just don't have to pump as fast. And our heart's the same thing. As we improve that stroke volume, it doesn't have to pump as fast to get the same volume of blood out.
Nice. Hey, little known fact.
Yep.
My grandmother's maiden name was Bello.
Really?
Bevinda Bello from the island of Madeira.
Yeah, that would explain a lot. So that's why you're always pumping out all this hot air.
It's the fiery Portuguese in me. The whitest Portuguese person in the world.
Today's episode of Fast Talk is brought to you by Alter Exploration. Created by me, Fast Talk Labs co-founder Chris Case, Alter Exploration crafts challenging, transformative cycling journeys in some of the world's most stunning destinations. A mantra is a powerful tool used to focus your mind on a particular goal and create calm during challenging situations. Our mantra? Transformation begins where comfort ends. This mantra isn't meant to be intimidating. On the contrary, it should be invigorating. For many people, everyday life is filled with convenience, monotony, and a lack of time spent in nature. Alter Exploration facilitates the exact opposite. Challenging, invigorating, life-altering experiences in the natural world. Alter's journeys aren't so much a vacation as an exploration of you and the destination. At the end of every day, be preoccupied as much by the transformative experience as by the satisfaction of exhaustion. Life altered. Learn more about my favorite adventure destinations and start dreaming at alterexploration.com.
Shall we move on to transport to the muscles?
Yeah, you want to talk about arteries and veins? What do you want to talk about?
Yeah, and again, this is a whole nother conversation, but there's a whole system, this whole network, the arterial system that takes oxygenated blood from the heart and gets it to the tissues that need it.
Remember, artery begins with A, and A stands for away because arteries carry blood away from the heart to the muscles.
Right. And venous system returns the blood. And
Yeah, I
remember
know.
V
for victory.
There you go. So we were victorious. And by the way, something we forgot to mention about the heart, it has two ventricles, two atrium. So there's the right and the left. The left is what pumps the oxygenated blood to the body. The right takes all that blood from the venous system, pumps it to the lungs where it can be reoxygenated.
You got it.
So, as we said, there's a lot that we can cover here, and we're probably going to skip over most of it, and it might be something we can cover in another episode. But you start with the arterial system, which actually you could see veins, particularly people that, you look at the bodybuilders, you see all those veins all over them. Veins are very flexible. They can expand and contract really easily.
They have like no structure whatsoever.
Right. So they're kind of floppy.
Mm-hmm.
Arteries aren't like that. If you pulled an artery out, it's actually kind of stiff. And it has a lot of muscle to it. And it is that way because it's trying to continue to create that pressure. So particularly as the blood is leaving the heart, the arterial system is very stiff to have a high pressure so that the blood gets driven to where it needs to get driven to, and you still have a good pressure gradient.
Right. And because of those muscles, then we're able to do things like open up, dilate, vasodilation, or close things down, which is vasoconstriction. And that is directing the blood within our body, right? We're eating. We want blood flow to go to our digestive system. So we're going to open up those blood vessels more than they are at rest. It's really cold outside. We don't want to lose heat through our extremities. So we're going to close off the blood to our fingers and toes so that we don't lose the heat there.
So there's another fact that I find really interesting.
Is it about your grandmother's maiden name?
Galbraith? No, not at all.
Damn.
Sorry. I find this kind of fascinating. Typical adult male has about 5 liters of blood in their body. Typical adult female, I think, is closer to 4 liters of blood in their body. But if everything is opened up, every capillary is opened up, the venous system is maximally expanded, we have the capacity to hold about 20 liters. So as Rob was just pointing out, we need to vasoconstrict some areas, vasodilate others. We kind of control where does that blood go to. Nothing is ever fully shut down. It would start dying, is my understanding, if that was the case. But you can really control where most of that blood is going, and our body ensures that it's going to where it's needed. So when you're at rest, it's really going to your organs and your digestive system, and the muscles just aren't getting very much.
Yeah.
When you're exercising, it'll actually shunt a lot of that blood away from those organs, which is part of why when you're going really hard, your digestive system doesn't start functioning very well. But a lot of it's going to the working muscles, and eventually will start going to the skin to dissipate heat.
Yeah, and this is a major adaptation for exercise, right? Is the creation of new blood vessels, arteries, but especially capillaries, arterioles. There's multiple levels of size here, kind of like you have boulevards and avenues and streets and alleys or whatever. But it's interesting that as we get all the way down to the capillary, which is essentially the smallest blood vessel, it's the one that's interacting with the tissue, right? Capillaries are interacting in our lungs. We have capillaries surrounding our muscles and everything else. The capillary itself is tiny. It is so small, like individual red blood cells can fit in a capillary. But there are so many capillaries that it ultimately creates so much volume that the blood flow is really slow through the capillary, which is going to help the offloading of oxygen. So it's just funny how, I kind of think about like, a capillary is kind of like angel hair pasta, right? And if you have just this big bundle of angel hair pasta, there's so much surface area in there, even though each individual tube is tiny.
So think of this like a river. When a river is narrow, water is going to move fairly fast. If the river widens out, the water slows down.
Exactly.
And so as Rob was saying, each capillary is very small. The total cross-sectional area of the capillaries is huge. So the blood really slows down, which gives the tissues, muscles, organs, a lot of time to take the oxygen out of that blood, which is really fascinating. And then you put in my notes, are you sure about this? But again, I got this out of McCardle.
No, and that's, if you notice, there's a red word right there, total, that I added. Because originally the note was large capillary cross-sectional area. And I was like, I don't know how I feel about that statement, but we actually agree.
Yeah. So the venous system that returns blood does not have the same cross-sectional area. So what you have is blood comes out of the heart really rapidly. It moves from the arterial system to the capillary system where it really slows down so that the tissues can take the oxygen out of the blood. And then it goes into the venous system where it actually will speed back up and get back up to the heart so it can go to the lungs.
Yeah, an interesting thing there, and I don't know, I think we ultimately need to do a whole episode on the cardiovascular system.
Yep.
But something that's interesting to point out, because the venous system doesn't have the ability to regulate its pressure, right? Just like the arteries, we said they have muscles. They can get bigger or smaller. They can regulate pressure because of that. The veins lack that ability. But what the veins have that the arteries don't is they have this series of one-way valves. And what that means is your heart pumps, it pushes through the artery, through the capillaries, through the muscle, and then into the vein, and that pushes it up the vein a little bit. But in between pumps, it doesn't necessarily move through the vein because it's not monitoring the pressure. So on the next heartbeat, it pushes it up a little bit more. The blood sort of ratchets up the venous system, and there are these little one-way valves so it doesn't fall all the way back down. And we know that we get pooling in our legs if we're standing for a long time or we're not moving, but this really helps prevent, pooling that could be much, much worse than it is.
To me, it's almost a design flaw in the body because, again, we talked, all this moves across a pressure gradient. And the heart, when it pumps out the blood, it creates a huge pressure.
Right.
So it's very easy for that blood to move to the tissues where it's being used. By the time it moves into the venous system, there's very little pressure left. So again, the way to think of this is like a hose. You put your finger over part of the end of the hose and the water is going to come out.
Squirting out, yeah.
Right. So that's what's happening when it's coming out of the heart. By the time it's returned to the venous system, it's like you take your full thumb off of a very large hose that doesn't have a lot of water flowing. There's not much pushing that water. And a lot of that blood is now below the heart. So it's got very little pressure driving it, and it has to now work against gravity to get back to the heart.
Yeah. The other thing that helps it work against gravity while we're on the topic, and this is Trevor's note, I will say, so I'm stealing his thunder on this, is the muscle pump and the pressure that happens from the contraction of the muscle itself, right? So oftentimes these veins are either running adjacent to a muscle or between muscle groups. Those muscles contract, they kind of swell and grow, just like my biceps do when I flex. And that squishes blood ultimately through the vein, and it can only smush it in the one direction because of those one-way valves. And anybody who's been in the military or had to stand at attention for a long time, you learn this sort of rhythmical contraction of your lower leg muscles to help, shunt the blood up towards your heart again.
Yep. It's so one of the ways you can tell somebody's cardiovascular health is edema in the feet, swelling of the feet. Because when the system's not working well, that blood's going to pool in the feet, and there's just not enough pressure. There's not enough of these systems working to return blood to the heart. And I'm going to use a bit of a gross example here, but I'm actually stealing this from McCardle, which is one of the really good exercise physiology textbooks out there.
Throw them under the bus.
Yeah, I'm throwing a little under the bus because he not only brought this up once in the textbook, or they brought
really
it up twice.
Wanted you, yeah.
Way that Romans obviously used to execute people was crucifying them. And the reason people would die on the cross was this. This is what would cause their death, because they're literally nailed to the cross. They can't use their muscles. They can't activate those muscle pumps by contracting their calves and their quads and all their different muscles to get that blood to return. So the blood would pool in their feet and their legs, and they would eventually pass out, and that would kill them. They wouldn't get enough blood to the brain.
Wow, look at that. There are other people like me that have kidney disease and don't have quite enough blood protein, and we get a little swelling in our feet and our shins too, but just saying, there's a caveat to your swelling rule.
That's fair. But the transport system is fascinating. Again, as you said, we could do a whole episode of that, but let's jump to now the blood has reached the muscles, and the muscles need to take up the oxygen. So let's talk about that. And we're going to focus on muscles here, but obviously all tissues in our body take up oxygen.
Yeah, but muscles are the only thing that matter.
Yes. And when you are exercising, when you are running or on that bike going really hard, it's something like 85% of that oxygen is taken up by those working muscles.
Right. And Trevor, a point that you had made earlier before we started recording is, it's a really interesting design that we have when we're talking about this pressure gradient system. Exercising muscles are using the oxygen that they have stored inside, right? And we're not going to get into it today, but inside the muscle cell is a molecule called myoglobin, which is analogous to hemoglobin. They're a little bit different. For all intents and purposes, they both carry oxygen. As that working muscle uses its oxygen, it has less oxygen, which means it has less pressure of oxygen than the blood flowing next to it. And that pressure gradient, your favorite thing, I'm just jumping on your bandwagon, sucks kind of the oxygen off of the red blood cell, out of the bloodstream and into that working muscle, where another muscle that's not necessarily working, or another cell that doesn't need it as much because their oxygen supply is doing okay, there isn't the big pressure gradient. And so you're not offloading oxygen to muscles or tissues, hopefully, that don't need it. And so it's really interesting how this passive gradient system is able to pick and choose. We say that like it's intelligent, but maybe intelligent design, depending on your belief system, the places that oxygen are going to.
Yeah. So what's really fascinating about that you're kind of implying here is, even though oxygen transports passively, there's no system that's forcing the oxygen across any sort of tissue.
It's not like that claw machine game, you can never win.
Right. This blood is passing by all the different muscles in our body. And if a muscle isn't really working right now, it's fully oxygenated, there's no pressure gradient. So that oxygen in the hemoglobin is just going to pass by. There isn't enough a gradient for that oxygen to pass to the muscle, or very little is going to pass to the muscle. Then that blood's going to reach a muscle that's working. And as you said, there's a much bigger pressure gradient. So all of a sudden that oxygen is going to be unbound from the hemoglobin and go into that muscle and be used. So that's, even though this is all passive, how the oxygen gets to the tissues that really need it.
Yeah. Something that I've always found really fascinating is that how strongly the hemoglobin wants to hold on to that oxygen molecule can actually be modified by some of the environments. And if we look at the condition at the muscle, right? Like let's pretend we're on the magic school bus and we're shrinking ourselves down. We're going through the vascular system. When you're parked right there in the vascular system next to the working muscle, what do you have? It's going to be hot, right? Muscles produce a lot of heat. It's going to be acidic because we have hydrogen ions that are being released from these metabolic processes. And there's going to be things like carbon dioxide that are escaping out of the muscle back into the bloodstream. All three of those can actually cause hemoglobin to want to hold on to oxygen less strong, to actually drop off the oxygen. So in addition to the partial pressure gradient, we have the hemoglobin kind of wants to get rid of it, to tell you the truth. Now we go all the way back to the other side of the body and the lungs. What's happening at the lungs? We're now breathing in cooler air. We're not next to a hot working muscle anymore. We've gotten rid of the carbon dioxide because we're blowing it out. And at this point, we've buffered the hydrogen ions, which means that hemoglobin has a higher affinity for oxygen and it wants to grab onto oxygen when it's at the lungs. Just kind of these little intricacies and nuances of how the body works they're absolutely mind-blowing to me.
It's really cool. I'm going to flip this around. Talk about altitude. One of the adaptations that we see in altitude is a minor change in the conformation of the hemoglobin that allows hemoglobin to bind more strongly to oxygen. The advantage of that is at the lungs, when unbound hemoglobin reaches the lungs and the partial pressure of the oxygen in the air is lower, the hemoglobin is going to have a harder time before you adapt to get all that oxygen out of the lungs. So you get this conformation change in the hemoglobin that allows it to take more oxygen out of the lungs at higher altitude. The issue is that conformation change makes it harder for the hemoglobin to release the oxygen at the muscle tissue.
Yeah.
So another actual adaptation that people don't talk as much about at altitude is a greater tolerance of acidity.
Interesting.
And one of the reasons is it allows us to use more anaerobic metabolism at higher altitude. But another reason is what we just talked about, that acidity around the muscle tissue is going to help the hemoglobin to release the oxygen.
Yeah.
That's called the Bohr effect, the temperature and pH. You threw it a name, I'm throwing out a name.
Yeah, more like the boratory effect, am I right?
Oh, God, that's the worst joke you've done to this whole episode.
The reason that carbon monoxide poisoning is what it is that hemoglobin actually wants to hold on to a carbon monoxide atom more strongly than it does to oxygen.
Right.
And so if you're in a place maybe with exhaust, maybe there's a malfunction of a system in your house, you don't have good ventilation, ultimately your hemoglobin can be saturated with a carbon monoxide, which is not useful within our body, but it means there's no room for oxygen anymore. So we're not actually able to supply the body with the oxygen that we need. Now, here's the tie to exercise. For a while, there was a xenon gas doping. Maybe there's people still doing this. I don't know. Apparently, athletes were going to junkyards in Europe and extracting the xenon gas out of the headlights of cars in junkyards. And the reason they were doing it was that xenon also has a strong affinity with hemoglobin. And so it's a similar effect to carbon monoxide, but not as strongly bound. And so in the right dose, athletes were breathing in xenon gas. They were ultimately lowering the oxygen saturation on their hemoglobin, on their red blood cells. The body was thinking it was in a hypoxic environment, like going to altitude, and it was creating more red blood cells. And after a few hours, I don't exactly remember how long, those xenons would fall off. The red blood cell would go back to being normal, but now the athlete, after doing this, would have more red blood cells. It's just amazing, like the lengths that people go to right?
Just get these little adaptations.
Yeah, exactly. So we got warm blood and we have xenon and we're superhuman.
Another one to quickly bring up, since you went down this road, is oxygen canisters. You do have endurance athletes at sea level who will sit there and suck on an oxygen canister, which is 100% oxygen.
Yeah. Live
Before their
low,
event.
train lower, man.
Yeah. So just remember, at sea level, your hemoglobin is 98% bound. It's about as bound as it's going to be. So that oxygen canister isn't helping the hemoglobin bound any more oxygen. It's a waste of money. That canister is going to help at altitude when hemoglobin is only 70, 80% bound.
We used to do a lot at Boulder Center for Sports Medicine of supplemental oxygen training. And you can push sea level power at altitude. And so for some select key workouts, it was a really interesting way to be able to do workloads you couldn't otherwise sustain in preparation for maybe sea level events. Yeah.
I think we got one last thing to cover here.
What?
We're still talking about taking up the oxygen at the tissue, so at the muscles. I think we just need to touch on AVO2 difference.
Go for it.
So this is, and it's a very hard thing to measure. They've pointed this out, that it's actually dangerous to measure this in an athlete. But there is the saturation of the hemoglobin when it leaves the heart. And then there is the saturation of the hemoglobin when it enters the venous system. Because tissues are taking up that oxygen, there's going to be a difference there. And that's called the AV difference, arterial venous O2 difference.
Yep. The extraction.
Right. And when you're at rest, when you're sitting there on the couch, we're not taking up 100% of the oxygen. We're only taking up about 25%. So yes, you have an AVO2 difference, but it's not huge. So essentially, the hemoglobin is storing oxygen. It isn't until we're exercising really hard that you start to see a bigger AVO2 difference.
I agree.
That's all you're giving me?
I don't remember what the numbers are off the top of my head. I did not prepare for that.
Thank you for being honest, Rob.
I was like, God, Trevor, just keep talking.
So
for the first time in my life, I wish that you just kept talking.
So why don't we leave that there? Because we have covered a lot. But that's really important to understand, is that difference is something that it's very hard to measure, but it's an important difference to understand. And I don't think there's ever a point where hemoglobin is 100% lacking oxygen.
No, I don't think it's possible based on the gradient system.
Yeah. So you're never fully using the oxygen that's bound. But when you start exercising, that AVO2 difference is going to increase. And that's actually going to help, because then when that blood, the venous blood, returns to the lungs, you're going to have a bigger pressure difference between the air in the lungs and that hemoglobin in the blood. And it's going to aid its ability to take the oxygen out of the lungs and to rebind all that hemoglobin, which is why even when we're exercising really hard, hemoglobin's going to stay pretty close to about 98% bound. Well, Rob, any last things that you can think of that we need to cover?
The only thing I can think is that we need more episodes on this. And I would actually love to hear, if you made it this far in the episode, do you want to hear more one-on-one episodes about different topics? Do you want to hear them about stuff we touched on here, but we said we couldn't do all of it, like the circulatory system, the full-on respiratory system? I'd love to hear from listeners, Trevor, to see what we should say next. And so for now, I got nothing else to say.
Listeners, this is a great time of year to expand your training knowledge. Join Fast Talk Laboratories now for the best knowledge base of training science on topics like polarized training, intervals, data analysis, sports nutrition, physiology, and more. Join Fast Talk Labs today and push your thinking and your training to all new heights. See more at fasttalklabs.com/join. To round out this episode, Rob, I got an idea. Instead of doing our 1-minute take-homes, I got to throw a question at you and I will answer it. When you were preparing for this episode, what was the most fascinating thing that you read or were reminded of?
For me, it's honestly how we shift the oxyhemoglobin to saturation curve using things like heat and pH and just, to me, the way that the body has evolved and how systems work together in concert with each other. you don't think about it day to day, but it's mind-blowing when you see the connections of how one thing begets another. And, everyone's like, hey, we don't want to produce hydrogen ions. That's really bad. And you're going anaerobic and blah, blah, blah. But if we don't do that, then it begins to affect the ability for us to offload oxygen. And it's almost like that butterfly effect. Like you kill that mosquito and suddenly there's no, so on and so forth, or bees and pollinators, and just how everything is interconnected within the world. It is that much more so within the body. What about you, Trevor?
Mine was really where we started this episode. And when I was reading McCardle again, they had a whole chapter on this, which is oxygen moves in our body by passive pressure gradients, which I find really cool because our body has this incredibly complex and intelligent system to make sure oxygen is always getting to where it needs to go. And it doesn't start failing or breaking down until we are going really hard. Until then, it is making sure that the oxygen is where it needs to be and whatever tissues are using it are getting the exact amount of oxygen they need. And that's really fascinating to me that it's all done with passive pressure gradients.
And that reminds me of the caveat that I didn't call you out for. I'm glad that you brought this up, Trevor. And that is oxygen moves through this passive diffusion because of the gradient of the partial pressures, but air does not move passively, right? And ultimately, we expend a lot of energy moving air in and out of our body. And this is where there's a lot of discussion on breath training devices, making that more efficient. We keep talking about an episode on this and maybe some work that Dr. Seiler has been doing. There are some coaches out there, Steve Neal in particular, who really believes strongly in this. It's an area that I actually don't know that much about, but maybe we should do an episode to force me to learn about it.
Yeah, and that's a really important point. When we're talking about air, we're talking about a gas. This whole conversation, when we were talking about oxygen, we were talking about those O2 molecules.
Exactly.
And where they're going.
Yep.
Well, Rob, I think we've hit the end of the episode. What's a really good groaning joke? Time to stop breathing?
I wouldn't hold my breath.
There we go. Thank you.
That was another episode of Fast Talk. Subscribe to Fast Talk wherever you prefer to find your favorite podcasts. Be sure to leave us a rating and a review. The thoughts and opinions expressed on Fast Talk are those of the individual. As always, we love your feedback. Join the conversation at forums.fasttalklabs.com or tweet at us with @FastTalkLabs. Head to fasttalklabs.com to get access to our endurance sports knowledge base, coach continuing education, as well as our in-person and remote athlete services. For the breathtaking Trevor Connor, I'm Rob Pickels. Thanks for listening.